It's coming soon at the time that I'm making this video. This one is literally and figuratively hot off the presses. It's a Xeon 6 server, but I promise you, you haven't seen a Xeon 6 server like this. 4 sockets, 64 DDR5 DIMM slots, up to 8 terabytes of memory in this chassis. This server is all about big memory, and I like big memory, I cannot lie. It's so hot off the presses, the air baffles are 3D printed. They won't be 3D printed in the final thing, but it's so cool. It's like, I get an early look at a 4-socket configuration. So these are Intel Xeon 6, 6700. The 6700 CPUs are actually available, certain 6700 CPUs are available in up to an 8-socket configuration, but this is the more mainstream 4-socket configuration in a completely standard 2U server. Get a little bit of extra depth on the quadruple 2700 watt power supplies, but this is 2 DIMMs per channel, and this is designed for applications like in-memory analytics and in-memory database processing and really high performance things like that. The chassis actually has a lot of configurability. The motherboard has a lot of configurability. It makes heavy use of MCIO, but this is Intel's kind of sort of secret weapon. I mean, companies like SAP, they have SAP HANA, I think is how you say that. And that is, you know, SAP is the largest enterprise resource planning company on planet Earth. And to do that, you need a database of your stuff and everything runs. And so SAP HANA is sort of like the next thing for in-memory databases. And this system was more or less designed to work with that type of an application. Scientific virtualization and hyperconvergence, because there is a lot of available PCIe Gen 5 connectivity, is really what this system is designed for. But let's take a closer look at our layout. Now, for a 4 CPU configuration like this, it is actually a little bit tricky in terms of system architecture and design and how you want to put it together. Because the Intel Xeon 6, remember, in a normal 6700 processor, I mean, we're talking up to 86 cores per socket. And you can have 2 pieces of silicon that are on an individual processor. So 2, 4, 6, 8 here. And in the default configuration, each piece of silicon is its own NUMA node. Now, NUMA is non-uniform memory access, and so basically the platform is optimized for lowest possible latency. And so that's telling the software, hey, this bank of memory is located really close to these processors. This bank of memory is located really close to these processors. This bank of memory is located really close to this set of processors. And so if you can think of the CPU itself as split down the middle, it's like this side is really close to this bank of memory. This side is really close to this bank of memory. And we have 2 DIMMs per channel, which is how we get the insane memory capacity. This is your only option. Intel is the thing that you have to run because of memory capacity. Intel supports multiplex rank DIMMs, MR DIMMs, and those are absurd capacity and absurd speed. And then they also support 2 DIMMs per channel, up to 5200 in the configuration in this chassis. And then you've got 4 sockets for piloting that. There are a lot of enterprise customers out there that are buying chassis like this because 2U is relatively standard. This is not really an exotic chassis. And the CPU is really just a vehicle for providing more memory channels. The CPU isn't really super important. The CPU is the thing that provides the memory access. And so then the CPU does become actually super important, but CPU as computation is not the important part. CPU as we need all the stuff. Intel accelerators, for customers that are relying on things like the Intel acceleration engines on CPUs, those 6700 Xeons can have up to 4 accelerators, whether we're talking DAA or other accelerators that Intel has on their CPUs. And so this is a great way to give you 16 of those accelerators in a chassis. These CPUs also provide a lot of PCIe connectivity, which we'll talk about in a minute, so they can connect to other storage, they can connect to storage, they can connect to more NVMe. And so for hyper-converged infrastructure, especially scientific compute and more high-capacity AI type stuff, this type of a configuration makes a lot of sense. There is no other platform you can get that has 64 DIMMs available to 4 CPUs. That can't be understated because I just need 8 terabytes of capacity. Supermicro has tested and qualified 8 terabytes on this platform. Theoretically, with higher capacity DIMMs that are coming later, Supermicro should be able to qualify 16 terabytes on this platform. That's on the Intel roadmap. But you physically can't get those DIMMs yet. At least, I don't think you can. They might be sampling, but I haven't seen them. I haven't seen them come up on the enterprise order sheet. This system is destined for something like an SAP HANA deployment. And so your SAP, your enterprise resource planning software, we need the fastest database option that makes the most sense. This is the most economic option, even though it is very expensive, because the database is going to run entirely from memory. And having 4 sockets gives you the ridiculous memory capacity. That's why this is built the way that it is. There are certain customers out there that have very specific requirements. SAP is definitely one of them, and this is what you get. But you also see these types of systems pop up in scientific scenarios where you're doing data analysis, things like radio telescope data analysis. The data is coming in at a certain rate, and you have to outrun the rate that the data is coming in. And a lot of the time, the easiest way to do that is to just try to locate everything as close together as possible. And that means lots of memory, close to lots of I/O, close to lots of very fast storage. And this is a platform that does that. Let's take a closer look at our chassis layout. Now, at the front here, we have 4 NVMe on each side. The best part of the U.2 on the front, toolless. Yeah, just pop the blue tabs. You can swap your U.2 drives all day long. No tools required. And if you look at the motherboard breakout, you can see that we actually have more extra MCIO connectors along the front edge of the motherboard. One imagines that Supermicro could be planning a version of this chassis that moves the fans from the front to the middle and gives you more NVMe I/O. But really, this is about I/O flexibility. You see, when you've got 4 CPUs, you may want to make certain decisions about where things are stored locally, where things are stored off chassis, and which CPU connects to it. As a system architect, the programmer working on some complicated thing may decide, okay, our first CPU in the system, we're going to try to route most of our I/O through that. So we will have our 200 gigabit AIOM. This is an OCP3 type module. AIOM is Supermicro's extension of OCP3. OCP3 supports some things. Supermicro adds a lot more options for that. So they have their own modules that are, this is PCIe 5.0 by 16 and a tiny little carrier card. And you can get these 400 gigabit, 800 gigabit, lots of fun connection. 200 gigabit here is what I have. And so you can choose to say the PCIe lanes for this go to this socket, and we're going to put our I/O on this socket. And our scientific compute is going to be pinned to our other 3 sockets, but the other CPU, the CPU 0, is going to be responsible for I/O. Other system architects might elect to say, we're going to distribute the I/O. We're going to have some of our NVMe connected to this socket, some of our NVMe connected to this socket, some of our networking connected to this socket, some of our networking connected to that socket. Certain peripherals support saying, okay, these 8 lanes go to this socket. These 8 lanes on this one physical card go to this other socket. More and more peripherals are showing up like that. And the reason for that is latency, because if this CPU is providing 16 Gen 5 lanes to one of the rear PCIe connections here, and this CPU needs to write out a bunch of information, it's going to have to use the UPI link from this CPU to this one to send it out. And the bandwidth really isn't a problem. I mean, it can create a bandwidth problem because there's bandwidth contention with other stuff going on in the system, I suppose. Generally, that's not an issue. The issue is latency. The extra hop from here to there, not great. If you have a cluster of these or you're doing scientific compute, the extra hop may be something undesirable. And so especially in network cards, especially DPUs, you have the giant network card that also has a compute actually on the network card. You don't want the latency. If you can avoid the latency, that's great. And a great way to avoid the latency is to have your network card connect directly to multiple sockets. Sometimes the chassis design is you just throw multiple network cards in there. So you have 2 of these in your dual AIOM modules in the layout here. And then you have some PCIe peripherals that also provide connectivity. And then you have 4 or 8 connections at the back. It's not about bandwidth. It's about latency. Latency is is quickly becoming one of the worst problems for building high-performance systems like this. And incidentally, latency is what has driven Intel to provide 4- and 8-way socket configurations, because some people need a huge amount of memory as close as possible, and that is why there are still 4- and 8-socket configurations that are linearly more expensive than systems that have 1 to 2 sockets. Meaning that if you just buy 2 2U chassis that have 2 sockets each, you're never going to get back to the performance that you have for those types of applications if you just have 4 sockets in a single chassis. If the workload can be split across multiple chassis, then getting multiple chassis for your workload is always the more cost-effective option. But if you need something that needs a huge amount of memory locally, the penalty for this CPU accessing this CPU's memory, not a lot, versus having to go out over the network or having to go out over any kind of a fabric interface or really anything through the PCIe bus. We're not technically using a PCIe interface to fetch cross-socket memory. This kind of a configuration is pretty common in scientific workloads as well for data processing, but in-memory databases are hotter than they've ever been, just because you can have an absurd amount of memory on a chassis like this, and that's why it is the way that it is. Now, if you need to route connections, that's what the MCIO connections are for. You can choose where your MCIO connection is going to go. You, as a system architect, can choose, okay, I'm going to move this over here and that over there. I'm going to rerun some benchmarks. And CIOs and CTOs, this is how you know you've got amazing people working for you. They're like, I think I could squeeze an extra 3% performance out of this if we just move our storage to be a little bit closer to data processing. And I've looked at the layout for this, and this thing is amazing. A lot of the time, your enterprise architects at SAP have done that work for you, and they say, we're going to use this chassis. This is how we've got it cabled. This thing belongs in this slot. This thing belongs in this slot. And the reason that they're putting things in specific slots is because they've done that kind of application level optimization, which is amazing. So bottom line, brass tacks, if you wanted to connect these NVMe to a different MCIO connector for some kind of an optimization like that, you could totally do that in this chassis. Let's take a look at our rear I/O, because there's more to talk about in the I/O and the power. So as you can see, we've got our 2700 watt 4 power supplies. Now you may be doing some quick math here. It's like, these are 4 CPUs, 330 watts each. 2700 watts seems like it's overkill. 64 DDR5 DIMMs. DDR5 uses a non-trivial amount of power. So you're talking about almost as much power in your DDR5, potentially, especially with those higher density DIMMs, than you are in your CPUs. So right now, you're already at your 2700 watt power budget just with the CPU and memory configuration if everything is running at full tilt insanity. Now, if you add a lot of PCIe I/O or other high performance cards, these are full height, full length slots. You've got at least 2 full height, full length. You've got 1 half height, full length slot on each side. That's another 1,000 watts per side, and now you've only got about 700 watts budget overhead. It is a 2+2 configuration, so ideally you have all 4 power supplies connected. You could lose up to 2 and the system will keep running normally, but really, hopefully, you know, if you lose 1, you go replace that immediately. But in a fully loaded configuration, there you go. And this is a 208 to 240 volt configuration only, unless you get, the DC version of this. Supermicro has the DC option for these power supplies. No problem there. But 110 volts, no, it's not. 208, your 3 phase from 208 or your 220. Yeah, it's going to work great with this chassis. Now, in terms of PCIe layout, you have 4 X16 slots, full size, 2 slots that are X8 electrical, all PCIe Gen 5. You have 2 M.2, those are PCIe Gen 4. And then you've got 2 AIOM X16 slots, that's PCIe Gen 5 by 16. OCP3 compatible, so if you wanted to use we've got the Intel fancy pants OCP3 module, hundreds and hundreds of gigabit in this connection. So yes, 6 PCIe slots, Gen 5, and they're not sharing lanes with anything. Full X16 in 4 of them, 8 lanes in 2 of them. That is an absurd amount of PCIe Gen 5 connectivity coming off of a chassis that has every CPU fully connected to every other CPU. That means that this CPU, if you look at the mesh diagram, those UPI links, this CPU connects directly to all 3 CPUs. It's not like a ring or anything like that. This is a fully connected mesh. But for as much horsepower as this system is, It's really not absurdly loud. And so that means the wiring on this motherboard is absolutely insane. It also has an onboard out-of-band management adapter, 2 USB, an RS-232 serial, a full-size DisplayPort, and the UID button basically just turns a blue light on so that you can find this in the front of the rack if you're working in the back of the rack. And there's a whole stack of these. And while we mentioned the DisplayPort in the rear, you probably also noticed VGA in the front. Makes it nice and accessible, and there's 2 USB ports right underneath the front latch. Very nice. In case you're wondering about the front of the power supplies, those are 12-volt breakout cables to be able to run high power peripherals. So if we did load a bunch of accelerators on this that need external 12-volt power, that's where we would connect them. Now in this configuration, we've got 3 high-performance fan modules at the front. That's going to push all the air that we need through the system, even for passively cooled accelerators that are running in the back. This chassis does support an alternative configuration where you could load a bunch more fans at the front here, but the larger fans that are located in the front module are a lot more efficient. These fans are a little physically smaller. We do have 2 smaller fan assemblies at the side, which is going to help direct airflow over the DIMMs and through the power supplies. If you want to read more about the flexibility and awesomeness of the motherboard that's in this chassis, that's the X14QBH+. But this chassis configuration is the 242H-NR. And this is shipping now. You can just buy it. Up to 86 cores per socket. But the thing that's really going to sell it? Lots of memory capacity. And to be sure, it's not just the memory capacity, it's also the I/O that goes with everything. Like, there is a certain amount of wisdom in providing lots of local resources to use to manage I/O to the memory, as well as PCIe. You could do this in a smaller number of sockets, but you're not going to get there in terms of memory bandwidth, and you might get there in terms of PCIe I/O. For a certain class of applications, this type of system architecture makes sense. Now, is there an opportunity for software designers to re-architect their software to work better across systems that have a lower number of sockets? Maybe, but we're not there yet. And this is quite a good system architecture and system design. Intel Xeon 6, as we've covered in our other videos about Intel Xeon 6, is the best Xeon that Intel has had in 10 years, bar none, hands down. And it's nice to see Intel still supporting their 4 and 8 socket configurations because, well, the competition in the market is really not doing that. It's not supporting that. It's, you know, on the one hand, it's like, is it necessary? On the other hand, I see systems like this that someday, when the memory is available, should support 16 terabytes of memory. Today, support 8 terabytes of memory. And that is a hugely impressive engineering feat to be able to manage error correction and everything that goes with 8 terabytes of memory in a system like this is just kind of mind-blowing. But enterprises are hooked on being able to run their entire database in memory. So that's why we have this. And it does that very well. And it's nice to be able to do that very well on a modern platform now that these CPUs have launched Q1 of 2025. So it's very, very nice to see. This is a first look. I can't get to benchmarks just yet because there's fun, new, interesting things about the Xeons. Like if you look at the Intel ARC page for these Xeons, they have certain cores that will boost all the way to a maximum frequency, but some of the cores are really only designed to be used when the system is fully loaded. So it depends on operating system and scheduler updates in order for me to get the benchmarks right. And so we're going to have to work on that in another video because that's a whole other interesting conversation. Yeah, you've got 86 cores, 30 of them, 36 of them or whatever, will run at the full speed. But when those are fully loaded, the other ones will come online, but the other cores come online and they don't come up to the same clock speed, you know, 2.1 gigahertz or whatever. Stay tuned for that full benchmark video, but I can give you a little bit of a teaser. We've got our memory latency checker here. This is an Intel utility that's going to show you the breakdown of NUMA nodes, and I've turned off sub-NUMA clustering, so every CPU is its own NUMA node. We've also got a nice little heat map here that shows the core-to-core latency across all the cores and all the sockets. And boy, this took a little while to run. With our system layout here, and sub-NUMA clustering is an option in the BIOS. So with sub-NUMA clustering on, each CPU shows up as 2 NUMA nodes. That's the 2 pieces of silicon that it has that are closer to one side of the memory or the other. With sub-NUMA clustering off, that treats each socket as its own NUMA node. So the memory that is close to a CPU is lower latency than the memory that's in another socket. It makes sense. It's just how much granularity do you want there? And yeah, that's a whole other conversation that we have to have in another video. This is just a quick system tour from Supermicro and a very, very early look because literally literally hot off the presses. Like the plastic is still warm, hot off the presses. So a lot of fun, and stay tuned for that. And that's gonna be in another video, and we'll take a look. But check out the link, 242H-NR. Just kick the tires, download the manual, look at the block diagram, have a lot of fun with that. It's like, it's here in the flesh. It is a marvel of engineering. There's no denying that. I'm Windowless Level 1, I'm signing out, and you can find me in the Level 1 forums.